a look at these. All right. So a linear one that crosses the x-axis. Girls, give me one. Y equals x. Good. Okay. All right, boys, one that does not cross the x-axis. Y equals 3. Y equals any constant. Good. Okay. 2. Girls, give me a second degree that crosses 2 times. X squared minus 4? Good. Oh, I thought you would have given it to me in factored form. But yeah, so that would be x plus 2x minus 2 if we looked at it in factored form. Great. Okay, boys, give me one that touches exactly 1 point.
Y equals x plus 2 squared.
Y equals x plus 2 squared?
Yeah.
Good. All right, one that does not cross the x-axis at all.
Y equals x squared plus 5.
Y equals x squared plus 5. Excellent. Okay, now we're moving on to cubics, 3rd degree equations. All right, girls, give me one that crosses 3 times.
Y equals 2x times x plus 3.
2x.
That's going to be on the
No,
test that we have.
2x squared.
Okay, we can't have a squared, but we could have like 2x, x plus 1, x minus 1. Will that work? So we've got a 0 at 0, a 0 at -1, 0 at +1. 3 different factors. 3 different factors give us 3 different zeros, cross the x-axis 3 different times. All right, fellas, twice.
Y equals x times x minus 1 minus
Good. Okay, so one of our factors needs to be squared, the other not. Okay? All right, once. Once, what would it be?
X minus 1 cubed.
X minus 1 cubed. Not at all.
Non-existent.
We can't do that.
You can't do that because this is an odd degree function, which means the end behavior, yeah, it's not possible.
X minus I.
All right. A 4th degree equation. Girls, crosses 4 times. What do I need? How many factors? 4. And it doesn't matter what they are. Any 4 different factors. Doesn't matter. All right? Boys, 3 times. One of the factors needs to be squared.
Squared.
And then 2 more.
X minus 1 squared. X plus 2.
Sure. All right, twice. Tell me about it. 2 of the factors must be squared. Once.
X plus 1 squared to the 4th.
X plus
Squared
to the
squared.
4th. X to the 4th. Squared to the 4th.
Squared squared.
He meant to the 4th. And what about not at all? Is it possible this time?
Yes.
Yes, because it's an even function.
To the 4th plus
X to the 4th plus 5. That'll do it.
Nice.
Excellent. Okay, any questions about our warm-up? All right, let's take a look at your homework. Okay, I just copied this. On my key, which I didn't really like pencil, so I couldn't copy it, there was an f of x at the beginning of each one of these. So it should have some kind of function notation there, but that's what we get when we multiply it all out. Let's see how you did.
I made it x plus 1 instead of x minus 1.
Painful.
I don't know why.
That's okay. Did you get all the rest of them right? If you did, you know what you're doing.
Just all the signs are wrong. pretty
Ooh, you forgot to subtract
much. No,
all the zeros?
it says x minus 1 up here, and I FOILed the x minus 3i, x plus 3i,
Uh-huh.
and then I brought it down, x squared plus 9, and then I just made it x plus 1 instead of x minus 1. know why. I was zooming through it, so that's probably why.
Gotcha.
Okay. We'll get everywhere else.
All right, let's go ahead and take a look at the bottom. Well, that won't be very helpful.
Yeah, Austin made it.
Okay, you can't see all of number 18, but number 18 we didn't class yesterday, so you don't need to see all of number 18.
Number 69.
I missed
Yeah.
Okay, if you got the majority of them right and only missed one, then you know what you're doing. You probably dropped a negative somewhere along the way, added 2 plus 3 and got 6. Those things happen.
I minus 1 and 4, and I got 1.
Let's just all hope they don't happen when you're being assessed.
Like the
That's when,
test,
yeah.
And then you forget to put a minus 5x.
Yeah.
This will be,
Yes.
This is going to be classwork, and then we have the page.
Yeah. Yeah.
It does look better.
Okay, for the most part, homework correct? Excellent. Okay, so now you know how to do two things. You know how to find all the roots of a polynomial given a complex root, and given all the roots, whether rational, irrational, or complex, we know how to find a polynomial of minimal degree. All right, so today we're going to tackle word problems. So if you'll take your blue workbook and open it to page 119, I want you to see what you can do with setting up the first part of number 9. Now, we've done most of this page already. We skipped the word problem on purpose. We were going to come back to them at the end, and here we are. So, page 119, number 9, I want to see if you can get the model set up for this volume. You can talk to each other. You can work together.
The depth is like how deep it is. So you have like the length. So if this was like the box, this would be the length, and then this would be the width, and then like
They just use depth instead of height.
that would be the box. Okay, or the depth. That stuff just confuses me.
Yeah.
You know what I'm saying?
Storage container.
It's actually unlimited storage.
Yeah.
Limited
in factored form.
unlimited.
Or do you want us to simplify
All right. You got it in factored form?
You have to paint your cap.
Okay, so it says that the compartment must be 2 meters longer than it is wide. So could we say the length is the width plus 2? And the depth must be 1 meter less than it is wide. So the depth would be the width minus 1. So these are my 3 dimensions here, length, width, and depth. And they define length and depth in terms of width. So in our equation, everything will be in terms of W, right? Because that's what they're all defined in terms of. So volume is length times width times height, or length times width times depth in this case. Multiply my 3 dimensions. So it's going to look like this. W times W plus 2 times W minus 1. Now this actually equals the volume, but doesn't it give us the volume in this problem? So instead of equaling V, we would have it equal 8.
Miss Willoughby,
Now,
how
yeah.
come you wouldn't have like a 2 or like a squared in there because you have like 2 length measurements? You know, like the 2 sides. Or you would just, it's fine. No mind. No mind.
All right, so to solve a higher degree polynomial equation, do we ever set them equal to 8?
No.
No, what do we set them equal to? 0. So the first thing we're going to have to do is multiply this back out and move that 8 over so that we can set it equal to 0. So if we distribute this W plus 2 through here, and then the W through the final, we'd get W squared plus 2W minus W minus 2. And then distribute the W through there. We get W cubed plus W squared minus 2W. And then we have to move the 8 over there too. So it would be minus 8 equals 0. Do we see how this equation models this situation we were presented with? All right. Now, it says list all the possible rational roots. So, possible rational roots are all the factors of the
1, 2, 4.
constant over all the factors of the A, leading coefficient. Yeah. All right. So, what are my factors of negative 8?
1, 2, 4.
Positive 1, positive negative 2, positive negative 4, and positive negative 8. Okay, all divided by what? 1. So do I even need to write divided by? No. So these, whoa. Oops. These are my answers. So that would be what we'd put on the blank here. That's it. Okay? Now, use synthetic division to find the roots. Okay, so we could test them out. If we plugged in 1, does that give me 0? 1 plus 1 minus 2, no. Plug in negative 1 plus 1 plus 2 minus 8, does that equal 0? Nope. Plug in 2, 8. Oh, there's an 8 that cancels with that 8, right? And 4 minus 4, isn't that 0? Yes. So we know that 2 works. So now we can do synthetic division with 2. What else could we have done using our technology to find that root quickly? Yes. We could have used the graphing calculator and just looked at negative 8 to positive 8. Where does it cross the x-axis? Good. All right, so 2 is our winner. It is a rational root. Now it asks us to use synthetic division. Please do it. Oh, wrong one. There. Okay, so did you get x squared plus 3x plus 4? Oh, how I wish the 4 and 3 were swapped because it would factor, but it doesn't. So what do we have to use? Quadratic formula. So we do negative b plus or minus the square root of b squared.
Minus 4.
Yes, very good. All over?
2a.
2a. So we get negative 3 plus or minus. Oh, 9 minus 16. Negative 7. So here I am getting imaginary, right? So if we're asked to list all the roots 2 was the first root, and we saw that by plugging that in, and we got out the 0. Then my other roots are negative 3 plus I root 7. That's not a 7. Try again. All over 2. And negative 3 minus I root 7. All over 2. So, are all the roots rational? No, they're not. We have 2 complex roots here that are not rational. The only rational root we have is 2. So, if we were thinking real world problem, what would the real world answer be? This 2. Okay, so what are the dimensions? Well, we know the width is 2, what were my units? Meters? Okay, so the length would be what? 4 meters. And the depth would be 1 meter. So those are the dimensions of my container. Yeah. Any questions?
So how did we know that 2 was the width?
It is my only real answer.
Okay.
Okay, so while you were checking homework, I passed out a little half sheet. So we have some more word problems we're going to look at today on that little half sheet. And we're going to approach them as we approach polynomial word problems. So, number 1, and you don't have the nice space because you can do it on notebook paper. Number 1 says, a farmer has 1,600 feet of fencing and wants to fence off a rectangular field that borders a straight river. So I'm very visual. So here's my river. Here's some type of rectangular field that borders the river. So because of the river, I really only need how many sides of this rectangle? 3. So we have these 2 congruent sides and this side over here. So here's my field in here that is bounded by my fence and the river. All right, so it says, what are the dimensions of the field that has the largest area? And that's all we have. So we have to work with this fence because that's what we're building, this fence. And how much fencing do we have? 1,600. That's all the fencing we have. Now, we know nothing about these dimensions. But we know that whatever the dimension of this side is, this would have to be the same. So what would you like to make it?
2x.
X?
Sorry.
Well, she got ahead of herself because she knew if there was an X here and there was an X here, and we're trying to determine this dimension, we know we have 1,600 feet of fencing to work with, and we've used up X and X. So what's this dimension?
2x.
1,600 minus 2x. That's what's left. That's how much fencing we have left to represent this side. Take a moment, see if that makes sense. Okay, so now that makes sense, let's set up an equation for this. And this is area, right? So we know area of a rectangular field would be length times width. So it would be x times 1,600 minus 2x. Now, before we do anything else, let's think about what would be an appropriate domain for this problem. Our fencing would have to be somewhere between 0 feet, because we can't have a negative amount of fencing, right?
Correct.
Up to
1,600.
It is 800.
let's look at our dimensions, our length and width. If x could go all the way up to 1,600, do you see that this dimension would be negative? Do we have a negative dimension?
Yes.
No, we don't.
800.
Have you ever measured a box and you got a negative 6-inch side? No.
It's on this trumpet thing in space.
Okay, well, when you start working math problems on that trumpet thing in space, then you can have some negative dimensions. But while we're still on Earth, we're not going to have any. So what is the largest possible value for x? 800. The acceptable domain is between 0 and 800. And if I graph this, guys, what would my zeros be? You can look at it. My 0 would be 0 and 800. And so I know it's going to look like this, and it's a what kind of function? What degree? It's a quadratic, and my leading coefficient is negative, so it's going to open down, so it's going to look like this, right? At the 0 and at the 800. But because the problem is dealing with area, this part really doesn't exist for us. In terms of our word problem, we're only looking at this part. Are we all together? Brian, are you back with me now?
Yeah.
Okay, great. All right, so here's our equation. And now, let's go back to what we're trying to answer here. What are the dimensions of the field that give us the largest area? Well, look at this little graph I made. What's represented by my horizontal axis?
The amount of fencing.
The amount of fencing. Okay, and what is represented by my vertical axis?
The area.
The area. So if I want the largest area, what do I want on this little graph? I want the vertex.
Which is 400.
Because the vertex is the max, and the vertex occurs halfway in between here, so it is 400.
Times 800.
Beautiful. Math all coming together for us.
Wait, how do we know it happens between these two?
When we did the quadratic unit,
That makes
and we found the zeros, we always said that the vertex is halfway in between the two zeros of a quadratic.
okay, I forget it.
Now,
It's okay.
all right, that's okay. Let's say you did forget that. What could we do on our calculator to find this? We could find the vertex using the maximum button, couldn't we? Yeah. All right, so we know that x is 400, so the dimensions would be 400 by 800. And that would give us the dimensions of the field using that amount of fencing that would have the greatest area. Okie dokie? All right. Number 2. A company needs you to design a box with no top from a square piece of cardboard. And before everybody laughs about this, I did have a friend at Tech that went to work for a company that all they did was create boxes. Some of the boxes did have tops, and he made an awful lot of money really fast
Creating boxes.
making boxes.
Everybody needs a box.
So, yeah, he
They're like flat rate boxes.
he created a system where it was much more efficient than the previous one, and so
What kind of boxes?
yeah.
Cardboard
So before we laugh about boxes, no, there can be money in boxes. All right. So here we go. We're starting off with a square piece of cardboard, and the company wants the height of the box to be 3 inches and the volume to be 432 cubic inches. So we're supposed to write a formula to represent the volume of this box if the side length of X of the original piece of cardboard. All right, so here is what we're starting with. A big square piece of cardboard.
With no top.
It's a square.
It's just a flat sheet of cardboard. And we are going to have to fold it to create the box.
Ooh. Can we use this?
Okay?
No, you have to.
Nope, you're going to tear it with your teeth.
Origami.
So what we're going to have to do to create the box, and most of y'all did this when you were like in elementary school and you thought it was pretty cool. You know, if you cut out the corners, then you can fold out the sides and it makes a box. And when you were little, you were like, wow. Now it's not such a wow moment. But that's what you do. You take this big square and you cut out little squares out of each corner so that you could fold it and create a box. Now, what did it say the height of the box needed to be? 3 inches. So on this picture, where would the 3 inches go if that was to give us the height?
The incision
What's
length.
where you cut?
The cuts, yes.
Oh.
All of these little squares that we cut out are 3 by 3s. Because when we fold that up, that gives us the height, doesn't it? All right, now, we did not know the original dimension here. They said call it x. But when we fold it up and we're talking about the volume of the box that's remaining, what we're looking at is this little part right here. So what would represent this little part right here?
X minus 9, 6.
X minus 6. Okay, what about here? What would this be? X minus 6. So, when we're doing volume, it's the area of the base times the height. Or, in this case, it's a rectangular box, so it's length times width times height. We know the height is 3. And the base is x minus 6 times x minus 6, which I could write as x minus 6 squared, right? Okay, so part B says, using this formula, what size of cardboard should you start with if you are trying to meet the company's needs? Well, the company needs the volume to be 432 cubic centimeters. So what do we plug in for volume? 432 cubic centimeters.
Why would the 3 be outside? What's that doing?
I could have written it like this. This is my height, this is my length, and my width.
Okay.
I'm multiplying those 3 dimensions.
Okay, okay.
Okay, now, many ways to solve this one, but when I see a coefficient out here that I can divide by, I'm always going to test and see if I can do that first because it makes my life easier. And I know this divides by 3 because 4 plus 3 plus 2 is 9, and that's divisible by 3. Yes, it's also divisible by 9. Yes. All right. So when we divide it by 3, what's that quotient? 144. Oh, how beautiful was that?
That's amazing.
Isn't that? Now, we know that the answer when I take the square root is plus or minus, but I'm dealing with length and width and height. And so what can I just eliminate? The negative, and we'll just go with a positive 12. And then I would move the 6 over, so 18 equals x. So the original piece of cardboard would need to be 18 inches by 18 inches so that we could create the box that we wanted. All is well? All right. I am not feeling this problem today, number 3, so we're going to skip it.
I love that.
Oh, this is great.
I mean, we might come back and do it. Don't mark it out or anything. We might do it as a warm-up on a not a Friday. All right.
Not a Monday either.
Okay, fair enough. Not a Monday. All right, here we go. Let's skip over to the next one, though, on that sheet, which is this one. All right. An open box is made from a rectangular piece of material. It's 15 centimeters by 9 centimeters, and we're going to be cutting equal squares from the corners and turning up the sides. So we're making another box from a flat sheet of cardboard.
We're going in the box.
We really could give them some competition in the box building, area. I'm with you.
The willow box.
Ooh, that's good. Ooh.
I like it.
I think you should give up teaching.
Copyright it now.
Willow boxes.
Copyright it, right?
I think so, but you came up with it, so I'd have to give you credit
I'll
for
give
it.
you permission. I'll take 2% of the profit.
Okay, fair enough.
I'll take 8.
Only 2%.
I
I would be like, I take 90.
I'll take for being here.
y'all are going to be on Shark Tank one day, and
All or nothing.
all right. So this one, we don't know how much we're cutting out. So it's kind of the reverse of the one we just did. Okay? But let's come up with what would the formula that would represent the volume of this be?
The same thing.
Similar. Yeah, it's the same process.
X minus 2x. X.
X is the height, so I'm good with that. Okay, what's my next dimension?
It's either 15, x, 15 minus
X squared minus
15 minus.
x.
Well, if this is 15, there's an x at this end and an x at that end. So it's minus 2x.
9 minus 2x.
And then 9 minus 2x. Okay, yes, this one said rectangle. Yes. All right, so let's think about an acceptable domain for this problem. Because that's really all we have to work within.
0 to 15.
0 to 15 is too big. That would give me a negative dimension.
7.5.
Still too big.
3.
3.
Why is 7.5 too big?
Because
Because it still gives me a negative dimension here, doesn't it? 4.5.
So like in the middle.
Hey, wouldn't it be like 4.5 and then a bunch of zeros?
Am I including either one of these?
Ah.
I did not. I did not include 0, and I did not include 4.5. It's everything in between that's part of our acceptable domain for this problem. All right. Now this one says find the dimensions of the box that will yield the maximum volume. Oh, you want your calculator now because this is not a quadratic. This is a cubic. And we know cubics can look like this. So there's no shortcut negative b over 2a. There's no shortcut vertex halfway in between. There's a thankful I have a graphing calculator to help me find the maximum.
It intercepts at 0.
It does. It will have one intercept at 0.
I got 10.
Yep. Yep. We know where the intercepts are. They're at 0. They're at 4.5 and 7.5. We know that's true. All right, grab your graphing calculator. Please find the maximum that occurs over our reasonable domain.
Wow. And you should change your battery. Maybe that's a good idea. Well, that's your problem. You're so welcome, really.
100.
I just see one line.
Window.
Still but high. I cannot zoom out far enough to see this.
Really? Did you set the window?
Oh, it's 1.82.
Yes. Look at that. Okay, so here's mine. I knew my x just needed to go from a little bit before 0 to a little past 4.5. So I made this part of the window. I cut my calculator off, but I made the x's go from -1 to +5, and I counted by ones. And then I just kind of had to play with the y's. First I made it to go to 50, and it still wasn't high enough. So then I made it to go to 100, and it still wasn't high enough. So then I went to 150, and I was there. So when I do that, I also change the counting number. I changed the scale, the y scale to tens, I think I did. And then I did left side, right side, finding the maximum, and I got 1.82. What about you?
Did you get line?
Okay, change your window. Go into window.
I was in window. It's got
Make your x's go from -1 to +5.
It's got
Count by
X min
ones.
and X max. Wait,
X min,
-1.
X max, X scale, or whatever it says here. Y min,
I got that.
-10. Y max, 150. Y scale, whatever this is, 10. And you should have a nice pretty window.
Oh, that's useful. I didn't do that.
Oh.
You see it now?
I did.
Yeah. And you know, when I graph these, I have to do just like you guys. I have to play around with that window till I get a nice pretty picture.
Why don't you just have it on like a really big setting and then you can
I think pretty soon, though, they'll have calculators that kind of work like iPads. They actually have the TI Inspire for the iPad, and you'll be able to, like, pinch.
Oh, that's
Yeah,
great.
wouldn't that be
How much
cooler?
does that cost? Like,
Wouldn't that be nice? Actually, the Inspire app is only, like, $40. Okay, how much was your calculator?
Good luck for Slater.
Nothing?
Yeah, but you can't use that. You can't use that on a test or anything.
No, you couldn't use an iPad on a test. But you could use it for lots of other things.
I don't
Alright.
need a
Apps are
calculator
like
for
99
pleasure.
cents or free or $1.30 or something. Not.
Well, they're not as cool as that one. Okay, so we got x was 1.82. So my dimensions are 1.82 by, did y'all get 11.36? By 5.36 centimeters.
So what exactly does that, like, the minimum represent?
The maximum?
Yeah, the maximum, like that.
Okay, what
the X
that,
value.
okay, let's go back and talk about it. What this represents is, this represents volume, the y-axis. The x-axis represents our x values for what we're going to cut out of that box. So, to get the biggest volume out of this rectangular sheet of cardboard, we should cut out 1.82 centimeters squares from each corner and fold it. That gives us the largest possible volume. Okay, now B. Find the values of x such that the volume is 56 centimeters. We're not looking for the largest, obviously, because we had 110 just a second ago. But we want the volume to equal 56 centimeters. So 56 equals this stuff. Now, hopefully all of you still have your calculators. And to solve this, what's the only thing we need to do with this equation?
Make it equal 0.
Make it equal to 0. So all you have to do is take that equation you currently have punched in and do minus 56.
Put in the equation solver.
Not the equation solver, you're going to look at the graph at the zeros. Now, because we set it equal to 0, now we can look at the graph and find the zeros. Because we made it equal, we forced it to. We forced it to equal 0. So we could look at the zeros on the calculator. And there are actually 3 of them. Did you find 3? Probably not. You probably only saw 2 because we set our window so that we could only look at the acceptable domain. There are actually 3. If you zoomed out, you'd see the 3rd one. You should have gotten 0.5. Did you get 0.5? Okay. You should have also found 3.5. And then probably none of you saw the 8 because you have the window setting just for the acceptable domain. But if you zoomed out, you would see that it also crossed at 8. But 8 is an impossible dimension because we would end up with negative dimensions if we cut out 8. It's not possible. Okay, so 8 is impossible. These 2 are acceptable. We could go either way. Yes, ma'am?
When you're like finding the zeros, do you like use the 0 setting?
Yes. Okay, I think that's going to be the last one we do today. Your homework is the workbook, page 120. But don't lose the half sheet. Stick it in your workbook or stick it somewhere. We'll pull it back out and tackle some of these that we chose not to do today as warm-ups later on.